The last video in this series is going to basically just kind of give you a bit of an introduction to the task in question number 5, and otherwise I'll expect you to sort of do most of it on your own. Basically because question number 5 is kind of a summary of all of the methods that we've used so far in this playlist, and all the different strategies kind of come together here. So this is a great opportunity to practice and to really start to see for yourself the difference between a left-hand sum, a right-hand sum, a midpoint sum, and a trapezoidal sum. There's also at the very bottom here, kind of hiding because it doesn't have a diagram, an opportunity to do the algebraic sum, which is the actual antiderivative of the function on the interval. So in this case, the antiderivative from 1 to 5 of the function 4x plus 12 minus x squared. So this would give you a way of kind of establishing a baseline for the areas, and sometimes I'll recommend doing the algebraic method first because that gives you a sense of expectation. That also tells you what the ideal answer to an area problem would be, so that as you're doing a left-hand sum, a right-hand sum, a midpoint sum, or a trapezoidal sum, you can kind of get a sense of like, okay, wait, was that a good estimate or a not so good estimate? Was there an overestimate or underestimate involved? And having something to compare your answers to is definitely helpful. So my suggestion is do the algebraic version first, so the actual antiderivative, plugging in the 5 and the 1 and evaluating, and then going back and doing the different types of rectangles. Now, just to make sure that you're okay with the setup, I do want to point out here that the interval is definitely from 1 to 5, and that the curve itself has been graphed for you, but we do actually need the curve. Remember that the curve itself dictates the y-coordinates that are going to end up becoming the heights of our various rectangles. So for instance, the left Riemann sum involves finding 1, 2, 3, 4 rectangles, each with a height that, if you notice it, touches the left-hand corner of the rectangle touches the curve, thus the name left. So you'll notice that the left Riemann sum is dictated by the left-hand corners of each rectangle. By contrast, the right Riemann sum is dictated by the right-hand endpoints or corners of each rectangle. So notice that by kind of focusing on those different points, you do end up getting very different looking shapes. And you can probably already kind of tell. The left one looks like it's going to be a bit of an overestimate because there's a bit of extra shaded space that we're going to calculate that looks like it goes beyond the curve too high. And the right Riemann sum looks like it's going to be an underestimate for a similar reason. Looks like some of these rectangles are simply going to be too low to give us an accurate representation. The midpoint and the trapezoid are probably going to yield the better estimates. So notice again which coordinates you're going to need in order to dictate those points, which thereby dictate the heights of each of your shapes. For midpoint, it's this sort of dotted, and it's hard to tell, but hopefully you can see it. It's that sort of dotted line that dictates the heights of each rectangle. And in the trapezoidal sum, it's the corner of each individual trapezoid that becomes the base 1 or the base 2 of your shape, depending on which one you're trying to calculate. Now, as always, pay close attention to the interval to dictate the x-coordinates, since you'll need the x-coordinates for the y-coordinates. In other words, if I label here 1, 2, 3, 4, and 5, that means it's probably going to be kind of easy for me to then either plug in 1 in order to find the y-coordinate 1 that will dictate a height of this rectangle, or I could do a table of values if I have access to a graphing calculator and just kind of figure it out that way. The good news is all of these shapes are set on the same interval, so whatever x and y coordinates you use for the first diagram, they'll be the same x and y coordinates for the second diagram. Just remember the same issue that we ran into before, where you'll definitely not be using the exact same x coordinates in each picture. For instance, on the left Riemann sum, we use the left-hand corners of each of the first 4 x coordinates, but 5 doesn't end up getting used. And hopefully you remember why. It's because when we try to draw a left-hand rectangle from 5, we'd extend beyond the interval into space that we're not being asked about, so we don't end up using this last coordinate. Same thing goes with the right-hand Riemann sum. If you start from the right-hand side and draw your rectangles, then rectangles, then rectangles, then rectangles, then you end up with an unused point here at x coordinate 1 that doesn't end up making a rectangle of its own. Again, because if you did try to draw a right rectangle here, you'd go beyond the interval into space that you don't need to calculate. So just be careful as you're transferring your coordinates from one diagram to the next, and make sure you're labeling things carefully. The midpoint is definitely the one that you'll want to pay the most attention to, because while the interval is still the same from 1 to 5, you'll want to pay close attention to the fact that the points themselves are not using 1, 2, 3, 4, and 5 as their x coordinates. Rather, the x coordinate of this first midpoint is found by using 1.5 and plugging in 1.5 to determine the y value that is the height of that rectangle. The second rectangle is the y coordinate of 2.5. The third rectangle uses the y coordinate of 3.5. And the last rectangle uses the y coordinate of 4.5. So again, a calculator might help here. A table of values that you can automatically generate in your calculator is a value, but either way, you can always just plug in your x coordinates to get the y coordinates from the equation if you have the time or the patience to do that by hand. The trapezoidal sum definitely uses all of the coordinates, and again, you can infer that the x coordinates are still the same. The y coordinates will indeed still be the same, so you can transfer many of your measurements or y coordinates from the left and the right hand diagrams over the trapezoid. Just remember to use the appropriate area formula for a trapezoid, which, as a reminder, is 1/2 base 1 plus base 2 times height. If you forget any formulas, definitely Google them just to make sure. Obviously, rectangles are pretty easy to remember, but if you learned trapezoid a different way, you might want to Google it just to ensure that you're remembering it accurately. In any case, this problem is now your responsibility to try to do so that you can try to practice all 4 methods. This is the last task for this set of problems, and it was kind of a lot. These were lengthy videos, and these were some pretty big ideas. So once you finish this page, I would suggest you just kind of let the ideas sink in for a little while. Give it some time before you start to do the next day's worth of problems and lessons, just because even though mathematically it's not like we're doing anything super rigorous, like it is just area problems after all, the numbers are quite tedious and there's a lot involved. If you are ambitious enough to work ahead, my suggestion is definitely to read a little bit of page 35, or sorry, page 33, I misspoke, because there's a bunch of kind of general theoretical stuff that may be worth kind of chewing on just for the sake of formality. If you don't feel like it's necessary right now and you just want to get the basic idea, I wouldn't worry about page 33 at all. But for those of us who do want to kind of move on to the big picture and start doing some real problems, take a look at page 33 before you moved into the next set of problems. For now, though, let's say that if you finish 32 and check your answers and you feel like you're in good shape, then you've done everything you need to do for this lesson. The next lesson, which is, again, on Thursday, if you're watching this on the dates that these were originally posted, should give you a little bit of time to just kind of see the actual context in which these problems would arise. So we'll treat that as a separate exercise. For now, let's say just get the basic ideas of the 4 types of geometric problems that you're going to solve. Make sure you know how to do regular old antiderivatives and check your answers. If you're good there, then you're good to go. You can do the quick check for this activity just to make sure the basic idea has sunken in. And then, of course, we'll resume with the next set of videos on a separate playlist next time you're ready to move forward.